My name is Noel Gorlick. I'm actually a noogler here, but I built Google Mars. I'm here to introduce Sean Raymond from the University of Colorado's Astrobiology Center. He's a NASA postdoctoral fellow, and he's going to talk about looking for habitable planets and stellar simulations.
All right. Well, it's a pleasure to be here. Thanks for coming to my talk. And I'll tell you guys today about some stuff we've been doing dealing with how planets form, how they evolve, and what are the chances for planets like Earth to form and survive around other stars. So starting off here is a completely artificial image I made showing 4 planetary systems. So on the bottom right is kind of a schematic of the inner solar system. So here's Jupiter, here's Earth, here's Mercury, Venus, and Mars, and the asteroid belt between Mars and Jupiter. So in the solar system, we have one planet that we know has life on it. We have liquid water on our surface. The temperature's about right for things like us to crawl around on there. All right, now here are 3 other systems that have been formed artificially in computer simulations that are obviously imperfect, but we think are a reasonable representation of reality. And so there's a lot of variety in other kind of planetary systems that could be out there. For example, this system up here on the top right has a planet that looks a lot like the Earth in it. But the system itself looks quite a bit different. There's a whole bunch, there's 6 or 7 Mars-sized icy planets out there. And there's no Jupiter. The giant planet out there is only about the size of Neptune, which is about 20 times less massive than Jupiter. Up here in the top left is a system that formed this planet right there, which is right at the right temperature for water to be liquid on this planet's surface. So you might think it's a good chance for life, this guy. But it turns out that during the formation process, it didn't actually get any water. So this planet right here is in the right spot for life, but it's got no water. So that kind of sucks. And down here in the bottom left is a system that looks a lot different than the solar system. We have a hot Jupiter. This thing is about Jupiter size, a big ball of gas. And it's very close in, very close to its star. Even closer, there's another kind of Earth-like planet, but it's really too hot. It's kind of like a hot Earth planet, way too hot for life. But exterior to that hot Jupiter is this planet. This guy's about the size of the Earth, maybe a little bigger, and it's got a ton of water on it. It's got maybe 50 or 100 times as much water on it as the Earth. So it's probably covered in oceans that are many miles deep. So the kind of things I'm going to be talking about today are how and where do Earth-like planets form? And when are we going to find planets like Earth around other stars? So that's kind of the stuff I'm going to be telling you guys about in the next, half hour, an hour or so. And before I get going, I want to thank NASA, who has provided me with funding to do this work for the last few years, and also to Noel for inviting me out here. So here we go. So before we get going, let me just give you guys some details about the solar system. This is kind of the thing I give to all these public talks I do. Just so everyone's on the same page here, we want to know what is going on in the solar system. So in our solar system, we have terrestrial planets close in, close to the star, close to the sun, and big balls of gas further out. The biggest planet in the solar system is Jupiter. It's about 300 times more massive than the Earth. And it's really the big, kind of the boss of the planets. It does most of the, its gravity really dominates the solar system. And then, the Earth is special, obviously, because we have life on it. And one other thing I forgot to mention is in this picture, right, the distances between planets are not to scale. The distance from the Earth to the sun is called 1 astronomical unit. And for example, Jupiter's out at 5 astronomical units. Neptune's out at 30 astronomical units. So, oh, right, I got this guy. So kind of to start off here, let's talk about how or where planets form. So here's an image of the galaxy. This isn't our galaxy because you can't really see our galaxy because we're embedded in it. But this is the closest galaxy that we think is quite similar to our own. This is the Andromeda galaxy. It's a big spiral galaxy. And if this were the Milky Way, because we think the Milky Way looks about the same as Andromeda, we would be kind of somewhere out here. Not in the center, not on the very edge, but probably about 2/3 of the way out, from the center to the edge of the galaxy. So that's about where we are. And the total number of stars in here is about, a few hundred billion. Not too many, a few here and there. So we're out there. Now, where do these stars form? We know they're forming in the galaxy somewhere. And they form in places in the galaxy called giant molecular clouds. So hopefully you guys are familiar with the constellation Orion. It's very bright up there in the summer sky right now. And so Orion's shield is out here, and this is Orion's belt. And if you ever look carefully, there's this little fuzzy thing in Orion's belt, and that's called the Orion Nebula. And when you look at it a little closer up, it looks like this. This is a young kind of star-forming factory. This is a big cloud of molecular gas. And each of these little clumps, they're kind of hard to see here, but little clumps in there are actively forming stars right now. And that's not the only one of these that's close by. There's another one, for example, called the Eagle Nebula. This is a famous Hubble Space Telescope image of one of these young star-forming regions. And so this is kind of these are the big, clouds of gas that are forming stars right now. In terms of planets, where do they form? Well, they form around stars, right? And so here's kind of a schematic image of what we think happens during the planet formation process, just showing a lot of things happening at once. Here's the stars right at the center in there. There's some jets that are magnetically thrown, vertically away from the star. And in this big disk of stuff, planets are forming. So for example, here, this is a young Jupiter-like planet that's forming, and it's got so much gravity that it actually carves a gap in the disk itself. And further in, you can see, there's more stuff going on. There's rocks that are colliding with each other to form bigger planets. And we think this is what's really going on. Up here is an image of a disk around a young star where we think this is what's happening in that disk. This lane right here, this dark lane, is actually dust, which is obscuring the light from the star. And so, most of the material is actually in there, even though it's the hardest part to see. And then the disk kind of flares out from there. And it's easier to see that outer part of the disk where it flares up. So there's a lot of things going on, during planet formation. To get from this cloud of gas to a system of planets that looks something like the solar system, it takes a lot of steps, and there's a lot of stuff going on. And I just want to kind of emphasize that, there's a lot of things going on, like gravity. There's things colliding to grow into larger bodies. There's all sorts of magnetic field effects and lots of stuff going on. And so what we're doing now is trying to look at little pieces of the puzzle independently to try to build the picture up together. But of course, there's lots of things going on, and they haven't all been put together yet. So, next, we know where planets form. Now, which planets could have life? What do you need to have life on a planet? Well, the answer is we don't know, because we only have one example, and so it's hard to extrapolate from one example, out to what you really need. But we can give it a shot anyway. The things that we really think are necessary are water, heat, and some kind of organic molecules to build your life. And so not only do you need just any old water, you probably need liquid water. The one thing that all life on Earth has in common is that it needs liquid water in some form. And so we think that's kind of a good place to start when looking for life around other stars. It could be that there's life that relies on something else, like liquid methane, I don't know. But liquid water seems a pretty reasonable place to start. And in terms of heat, there's lots of different sources of heat out there. And the one I'll be talking about most is just the very simple thing that is kind of intuitive, which is heat coming from the central star. So when you're further away, it's colder, and closer to the star, it's hotter. Very simple. So where does this happen? Where do you get this mix of ingredients? And the place that this happens is called the habitable zone. So this is the schematic of the solar system with the sun with lipstick right there. And so there's kind of an annulus, this ring of distances from the star where the temperature is right that you can have water as a liquid on the planet's surface. Too close in, it's too hot. Too far out, it freezes out into ice. The trick is, in order to have life, like I mentioned before, you don't just need the right temperature. You actually need to have water as well. And so this is actually the universal symbol of life on a planet right there. So, a happy planet anyway. So, you need water. So it turns out there's a little catch-22 in terms of forming a planet in the right place for life and with the right composition. So on the Earth, for water to be liquid, it has to be hotter than about 0 degrees Celsius. But the Earth formed in this disk of gas and dust, and the pressure is very low in there. And it turns out that in these low-pressure environments, ice condenses at a much lower temperature. So to have ice form, it has to be actually colder than about negative 100 degrees Celsius. And the only way to get water on a planet, we think, is for it to be impacted by icy bodies like comets or asteroids. So that means that your planet that's at the right temperature for liquid water is too hot to actually have any ice on it or have any water on it. Right? That means that these building blocks here, the stuff that planets are formed of right around here, is actually dry. And so how do you end up with a planet in the right place that also has the right composition? And that's kind of the catch-22. And the way that you do it is actually by mixing during formation. So this is kind of a schematic of close to the star, close to the sun, things are mostly rocky. Further out, they're mostly, part rock, part ice. And on this picture, the habitable zone will be somewhere in here. So, we're in the rocky zone, but we want some water as well. So how do we get that? Well, you got to mix these two regions up a little. So that gets the whole issue of how planets form. And this is kind of a schematic of the disk from which we think that the solar system formed. And so like we saw before, it's kind of colder further out. And the stuff that you have to build planets is different in different places. So very close to the star, you got metal and rock. Further out, you get some water. Because water is volatile, but not really volatile. And further out, you can actually build planets out of things like carbon dioxide, methane, and nitrogen, things like that. So, how does this actually happen? Well, it happens in a bunch of different stages. And I won't go into too much detail here, but there's various stages in the process because you're starting from tiny microscopic grains, and you end up with planets as big as Mars or Earth. So how does that happen? Well, first the grains kind of settle to a thin region in the disk, and then they grow via several different steps. So for example, here's a simulation showing snapshots in time of larger bodies, bodies growing in this disk of kind of starting from things that are about a mile across and ending up with things that are about the size of the moon or so. And so that process takes maybe a few 100,000 years, maybe 1 million years or so. And then the real building of planets like Earth is starting from these kind of moon-sized things and building those by gravity and collisions into things as big as the Earth. So how does that happen? Well, here's a very simple little thing to remind you about orbits, in case you're not familiar with them. So you're going to see these words semi-major axis and eccentricity a lot coming up in the next few slides. And so just to remind you, semi-major axis is just the average distance between an orbit and the star. And the eccentricity is how elliptical it is. So circular orbits have 0. Very elliptical ones have larger numbers between 0 and 1. And so for things to collide, you need to have some eccentricity. Because if you have a whole bunch of circular orbits, they never intersect. You can't collide. So for example, if one of these guys in the middle suddenly magically got an eccentricity of 0.5, then its orbit would cross a whole bunch of other ones. And then you can have collisions between bodies. Okay? So here's a little movie of planets growing. And so just so you guys know what's going on here, we got eccentricity and orbital distance. And the colors represent composition. So red means dry, and blue means 5% water in this case. And so 1 is the Earth-Sun distance. The sun is here at 0. And there's actually, Jupiter's actually in this simulation as well. It's just off the edge of the graph. It's out there at about 5.5 astronomical units. So here we go. So you can see very quickly things are starting to happen. And up here, by the way, is just the time going by in mega years, so in millions of years. So planets kind of grow. They tend to grow faster closer to the star where orbits are faster. And you can see for most of, for the first 10 or 20 million years, everything that's in the inner disk stays red, and this stuff out here stays blue. There's still no water. This guy here is growing. At this time, it's about the size of Earth. And you can see it's still red, and then at some point, there, it just changed color. What that means is that it got impacted by something that started off out here, whose orbit got changed and eventually made its way into the habitable zone, which is, at around 1 astronomical unit or so. So these 3 planets formed relatively quickly in maybe 30 or 50 million years or so. And then we have this belt of asteroids, similar to our own asteroid belt, which is kind of slowly clearing out And so it takes 100 or a couple hundred million years for things to happen. At the end of that movie, there were 3 planets. The one that formed right around 1 AU was about the size of the Earth. It was a little bigger, about 2 Earth masses, and it had a bunch of water. It had about the same water as the Earth or so. The Earth on this scale is about kind of green or so. So what happens if you do this a bunch of times, then you get a whole bunch of dots that have different colors. So what you really get is that you get a large variety of outcomes, like I was alluding to earlier. So you get a large variety both in terms of, oh, go ahead.
Did most of the original mass wind up in the planets, or did it escape?
In that case, it was about 50-50. About half of the mass went into planets, and about half the mass ended up getting ejected mostly by the giant planet. But it varies from case to case depending on the configuration of the giant planet and the disk. So in terms of this, there's a whole bunch of variety in terms of outcomes, both in terms of what the planets look like. So each of these is the outcome of a simulation with a solar system for scale. In each of these cases, a planet formed on an orbit very similar to the Earth's, so in the habitable zone. So that's the one that's close to 1 here. So for example, this guy right here is the planet that formed at about the same orbit as the Earth is, but completely dry. It didn't get any water during formation. This guy down here is unusual in that it's very large. This planet's about 3 times as massive as the Earth, and it has a lot of water, about 20 times more water than the Earth. And this guy up here, for example, this planet is very similar to Earth, but the system itself looks quite different. So that image I was showing you at the very start of the talk is a different way of visualizing this stuff. So taking a few of these outcomes and then making them into something that looks a little prettier. Just trying to get the point across. You have a variety of outcomes in terms of the planets themselves and also the context, the system of planets that they're in. And in addition to just seeing variety, we also see kind of some systematic effects. For example, in cases that look like our solar system, you have a giant planet, Jupiter, out at 5 times the Earth's sun distance. What happens if its orbit's a little different? Oh, you got a question?
Yes, do you assume a planar orbital situation there?
There's a distribution of inclinations, which are, so they're not in exactly the same plane. They're in a relatively thin plane to start, but not exactly. So there's, it's 3-dimensional and all that.
Does it converge to a plane ultimately?
It depends on the case. It can, in most cases, it converges where all the planets are within a few degrees at the end, but not always. So one systematic effect that's quite strong is that the eccentricity of the outer giant planet really affects what's going on with Earth-like planets. And why is that? It's because its orbit ends up coming a lot closer. So for example, the star here is this, the black dot there. And each of these circles represents more or less the orbit of the Earth, say. You can see if the giant planet's on a circular orbit, then all this material, it stays relatively far away from the Earth, and it's not intersecting the orbits of this stuff, this asteroidal stuff, which is what supplied the water to the Earth in the first place. But if its eccentricity is pretty big, then it does. It's kind of interfering with the process. And all this water-rich stuff that would have ended up on a planet like the Earth instead gets chucked out. So if you have a nice circular orbit, which is similar to Jupiter's orbit, although Jupiter's orbit is not perfectly circular, but relatively circular orbits of giant planets kind of help water be slowly delivered to planets like the Earth, whereas if they're very eccentric, then it disrupts the process and chucks out most of that water-rich stuff. And so what you have left behind are planets more like Mars, which are relatively dry and relatively small. So there's lots of different correlations like that, but this is kind of a very strong one, a very clear one. So now how do we actually go about finding planets around other stars? You guys have probably heard that about 250 planets or so are known right now. Most of them were detected by this technique, the radial velocity technique. And so what's actually measured is the wobble of a star in response to the orbit of the planet. Simply, the planet and the star are orbiting their common center of gravity. And so the star itself is wobbling with a certain velocity. And so by measuring the wobble of the star towards or away from, basically towards or away from us, we can figure out that there's a planet there. And it's pretty incredible. The precision of the current instruments is such that they can detect the radial velocity of a star, which is 10 or 100 light years away. They can detect that velocity down to actually about a foot per second or so. So kind of a slow walk across the room is how fast, how well they can measure the speed of a star 100 light years away. It's pretty incredible. And that's the kind of precision you need to find planets like the Earth, actually. So that's one technique. This has been the most successful technique to date. Here's another technique which is really picking up now. It's called looking for transits. Basically, as a star passes in front of as a planet passes in front of the disk of a star, from our line of sight, the brightness of the star dips. And it dips periodically once per orbit of the planet. And so by basically by monitoring the brightness of many hundreds of thousands of stars, then the planets whose orbits happen to be lined up just right, will cause this kind of signal, and you can pick that out. And so currently, I think about 20 planets are known to transit. And there's a couple upcoming missions that are going to really clean up using this technique. They're going to be space missions, and so they won't be restricted to only observe during the day and be confined by weather and things like that. They're just going to stare at a given patch of sky at about 100 or 200,000 stars, nonstop for 5 or 6 years, looking for planets like Earth. And so it's pretty exciting. So what have we learned so far from these planets that have been found? Well, about 250 planets have been found. As of Saturday, there were 248 planets known outside the solar system. And there's a lot of weird planets out there. Most of the ones that have been found are the big ones because they're easier to find. The vast majority of these are Jupiter-like. So they're big balls of gas. They're not, little rocks. And their orbits are really different than those in our solar system. So for example, if you look down here on the bottom left, in yellow are the orbits of the terrestrial planets in the solar system, so Mercury, Venus, Earth, Mars. And in red are orbits of 4 known extrasolar planets. And so these are not, the red ones are not from the same system. They're from different systems, but kind of showing the variety of orbits that are out there. There are some really close-in ones, like ridiculously close in. Those are called the hot Jupiters because they're like Jupiter in that they're big balls of gas, but they're ridiculously hot because they're right next to their star. There's a lot of really elliptical orbits out there too, really eccentric orbits. So I'll talk in a sec about that. So for example, each of these dots showing the kind of orbital distance versus eccentricity, each of these dots is one of the known planets. And you can see there's a lot of them up here that have significant eccentricity. All the planets in the solar system have eccentricities below about 0.05 or 0.08 or so. But in a few cases, there are planets that look something like the solar system. For example, in this top right, this system called 55 Cancri has one planet whose orbit is very similar to Jupiter's, its outer planet. But it turns out it also has 3 hot Jupiters as well. So that planet, that system 55 Cancri kind of looks like the solar system and unlike it at the same time. It's like it because it has one planet like Jupiter, but unlike it because it has a bunch of planets that are really unlike Jupiter. Sorry, there's a question in the back?
Is this eccentricity distribution to do with our measurement method, that it's easier to see the more eccentric planets?
No, it's not. These are well-established eccentricities. But it turns out it is, as more data on a given planet are gathered, eccentricities do tend to go down a little bit, by a couple %. But it wouldn't affect the overall distribution.
The question was, is there something bias that makes it higher eccentricity easier to detect?
It's much easier to detect things that are closer to the star, but it doesn't really make a difference if they're more eccentric or not. So, any other questions? Yeah?
Yes. Older systems would tend to have lower eccentricities. Is that a fair statement?
No, not usually. Any system that's older than a few million years has a similar eccentricity distribution, we think. And it turns out that after a given time, then you have more time for planets that are in the system to go unstable. So you might expect that further on, more older systems will have had these instabilities, but the fraction of those that will have such instabilities is probably pretty small. So it's moderately true that old ones will have more eccentric orbits, but not to a large degree. Okay. So that's kind of what we know about extrasolar planets so far. And so in terms of these Earth-like planets, the weirdos that we saw were these hot Jupiters and the really eccentric giant planets. So in the context of those guys, can you have Earth-like planets in those systems as well? So one of the main models for how eccentricities grow in these things, so where do these large eccentricities come from, is the idea that you have an instability between systems of planets that formed on more or less circular orbits. So in this case, 3 planets formed around the system. Those outer 2 just interacted. One of them got chucked out, and the one that's left, you can see it's on a very eccentric orbit. And so we think this is probably how lots of large eccentricities came about. And so the time scale for this to happen is longer than this 100 million years that's here, or sorry, 100 years here. It's probably more like millions or hundreds of millions of years. But the same process is probably responsible for at least a large fraction of the very eccentric planets. So it's kind of neat. They have a little dance in there, and then one of them gets chucked out like that. So, yeah.
So what happens to this planet that gets tossed out?
It depends. If it has enough energy, then it's completely gone from the system. Otherwise, it might remain on a very wide orbit. It just depends on the energy of the kind of last strong encounter it had with the other planet. So in the context of that, one thing that can happen, this is not the case in all the time, but one interesting thing that can happen is this thing called planetary system suicide. So imagine a system where, actually not too different from our solar system, imagine you have Jupiter and Saturn there in black. These black lines are giant planets, and you have a nice Earth-like planet that formed. But imagine that Jupiter and Saturn's orbits were a little bit closer in, such that they're actually unstable on a long time scale. They're unstable on a time scale that's much longer than the formation time of the Earth-like planet, though. So the Earth-like planet forms, everything seems happy, but then these 2 guys have a close encounter like we just saw, and one of them gets chucked out. And what's left behind would be something on an eccentric orbit. And it turns out that in most cases, it depends on the exact configuration of everything, but in many cases, the Earth-like planet in that case would be destroyed. So does this really happen? Well, we don't know for sure, of course, because we haven't been able to watch this happen around another star. But there's some evidence that it could happen. This is that distribution I showed you before. And this box up here are planets that would be able to form a planet like Earth if their eccentricity started lower, and then in some impulsive event got knocked up higher. So we think this is kind of one of the many processes that can happen in terms of planets forming, evolving, and killing each other. Now here's, what about the hot Jupiter system? Well, we think that hot Jupiters actually don't form where they are. These are these really massive things really close to their stars. We think they probably form further out, maybe around where Jupiter is now, and then migrate inward. How does that migration happen? It happens by interactions between the planet and the disk of gas from which it formed. And so here's a little schematic of that process. The star is embedded in there, and this is the giant planet right here. And it actually has enough gravity to carve out a gap in the disk. And then interactions between the disk and the planet tend to push the planet inward, and it can end up being stopped very close to the star, something like 1/10 or even less than that, maybe 5% of the Earth-Sun distance. So basically, they form further out and move inward. Neat little animation. So as they migrate inward, the trick is they're migrating right through where planets like Earth are trying to form. And the question is, what does that do to planets like Earth? The naive answer, and the answer I thought was the right answer until recently, is that it screws everything up and the chances for forming Earth-like planets are gone. But it turns out that's not actually what happens. So here's another movie. In this case, the same as before where the colors represent composition. In this case, this is a giant planet that's migrated through this disk of stuff. And this time is in thousands of years now. So this guy is artificially being pushed inward. And what happens? Well, these vertical lines are actually special places. They're called resonances. Each, at this one here, the orbit of each of those guys is exactly half that of the giant planet. The orbital period is half of that. And that turns out to be a special place where eccentricity is excited a lot. And because of these resonances, some material can actually be pushed inward, and some ends up getting a little too close to the giant planet and gets scattered outward. And so after this thing plows through this disk of stuff, a bunch of material remains in here and a bunch out here. And so the question is, this is a relatively short movie. Half of this material ended up getting pushed inward, and these are planets, kind of what I would call hot Earth planets. So Earth because they're rocky, and hot because they're really close to the star. And normal Earth, planets that might have life, would be out here around, around 1 astronomical unit. But, there's all this crazy stuff out there, and can that actually form planets like Earth? It's not obvious. And so I have another movie to show you that they can. So here's the same kind of thing happening. That migration happened really fast because instead of going for 100,000 years, we're going for a couple 100 million years. That the giant planet moved all this material in here. We got 2 hot Earths in there, and all that stuff out here. And because of interactions between the disk of gas and these growing protoplanets, eccentricities got damped, and things proceeded in a way that was not too different than before. And so at the end of this movie, there's actually 2 large planets that have formed. There's one of these that's a hot Earth. This guy's about 4 times as massive as the Earth. And this guy out here is about 3 times as massive as the Earth. And kind of the most striking thing about this planet here is it's in the habitable zone. It's at the right temperature for water to be liquid. But it's a lot different than the Earth in terms of its composition. It has actually about 50 times more water than the Earth. So more or less the same size as the Earth, but something like 50 times as much water. So what does that mean in terms of what the planet looks like? Well, maybe this is what it looks like, right? We don't know. This is an artist's conception of what the planet might look like. This is the view from that planet that's covered in water, that's in the habitable zone at sunset, because that's the best time for these kind of artist impressions. So the sun's just setting there. You can see this is that hot Jupiter. Even a little speck in there is that hot Earth planet that also formed. And the surface is probably covered in water. On the Earth, storms get really big over water, and they tend to peter out over land. And so on a planet that's just covered in water, you might end up getting really big storms. And so we decided to throw in a really big storm as well. But the storm couldn't be so big as to block the view, so it's kind of just approaching. The timing is just right. That's a question?
I'm sure you can't give that reasonable answer to this question, but how much do you think the oceanic depth would affect how habitable a planet would be at a given orbit? I mean, if the ocean is so deep that you have to be like the freezing cold, crushing depths of the Earth ocean or worse,
Yeah, that's a tricky thing. Is some people think that ocean-covered planets are not actually good places for life because the surface of the planet actually keeps the ocean in touch with the atmosphere. There's erosion from rainfall and such that gets fed down into subducted plates and so on. And that actually has long-term consequences for the climate. And so, what would happen on a planet where you don't have that interaction? You're not able to basically to erode away this material on the surface. And no one really knows the answer. So lots of people are thinking about that, but it's still pretty theoretical. And where could life exist? In the oceans? I don't know. This is actually probably pretty similar to the situation on Europa, which is a moon of Jupiter. In that case, we're pretty sure that there's a relatively thick ocean of water, probably the kind of salty water, underneath the surface of Europa. The surface is ice, and the depth of the ice is something like a few kilometers. And then you have a layer of maybe 50 or 100 kilometers of water, and below that you have rock probably. And people have been thinking a lot about whether life could exist on Europa as well. And so the real answer is no one knows for sure, but there's lots of these feedbacks that are really nice on Earth. And the fact that you probably don't have them on these planets surely plays a role in there. And we're not exactly sure how important it is. But even though we're not sure that life could exist on these planets, we decided to speculate about what it might look like. And we thought it might look like one of these crazy guys there. We actually did that to get on a blog, a marine biologist blog, because it worked too. Okay, so now in terms of looking for these planets, when are we actually going to find a planet like the Earth around another star? And the answer is we may have already done it, and I'll mention that in a sec. But here, let me just kind of highlight some upcoming missions that you guys can look for if you see things in the news. There's these radio velocities, kind of wobble technique searches. Those are ongoing. Those can find planets that are a little bigger than the Earth. There's these transit missions looking for the eclipses of planets going around other stars. And then there's a whole bunch of other kind of crazy missions that are, 10 or 20 or 30 years away that are hoping to not only find such planets, but actually look in detail, maybe get a spectrum of the planet, try to learn something about the planet's atmosphere, and if we're lucky, something even about its surface. So a long ways away from knowing the details of everything that's going on the surface, but looking for some kind of signs of life on them. So I mentioned that we may have found a planet like the Earth already, and that's this planet called Gliese 581c. There was a big press release about this in April, and this star is right here. This is a map of the constellation Libra, I guess. And so this star is actually quite close to the Earth. It's only about 20 light years away, but it's what's called an M-dwarf star. It's a red dwarf star. It's about 30% as massive as the Earth, and it's only about 1% as bright as the sun. Oh, sorry, it's about 30% as massive as the sun, and only 1% as bright as the sun. And so even though it's very close by, it's very faint. So it's this little faint blip there. And so the Swiss team used the radial velocity method to find some planets around this star. And actually, because the star is not very massive, as the planet orbits the star, the wobble induced by the star is larger. So in some sense, it's easier to detect because the wobble is larger, but it's harder also because these stars are intrinsically fainter. So it's kind of a trade-off thing. But the big press release was most Earth-like planet yet. And initially, they claimed that this planet was like the Earth, had the right temperature, was in the habitable zone and all this stuff. And I'll tell you guys in a sec that was probably wrong, but it's close. It's very close. And so kind of the details of this planet are that this planet's about 5 times the mass of the Earth. It's in a system of 3 planets that are currently known. The inner one's about the size of Neptune, which is 15 Earth masses. Then the next one out is this one that was claimed to be habitable, which is about 5 Earth masses. There's one that's even further out that's about 8 Earth masses. And it was initially claimed that this planet C, which is the middle of those 3 planets, might be habitable, might be in the habitable zone. But it turns out they were wrong. It's probably more like Venus than Earth. It's about 50% hotter than it is on the Earth. And so, at least in terms of our current thinking of the habitable zone, it's probably too hot. But it's pretty close. It's within 10% or so in terms of its orbital distance to the habitable zone. And the fact that they can find one that's so close means they can probably find one that's in the habitable zone. And if this planet were a little further out, it would still have been detectable. What does this planet actually look like? Well, no one knows for sure. It's probably something like 50% bigger in size than the Earth. And here's a little artist's conception of what it would look like from this planet. With the red dwarf star and another planet close in, and then the other one further out. So kind of the main message here is that we can find these planets that are a lot like the Earth. Can't find ones that are quite as small as the Earth yet. These ones that are a little bit bigger. The situation is not quite the same. They could not have found such a planet orbiting a star like the Sun with this technique, at least not yet. But because it was a relatively low mass star, the habitable zone is much closer in because they're fainter. And so they were able to find this planet. And if that one's there, then there's probably a whole lot more that are on similar orbits, but maybe a little further out. And it'll be really exciting when they actually do find one that stands up and is really like the Earth. And so kind of what's next in this kind of field is we're kind of putting more pieces together, trying to get the general picture of when things happen and how they happen, and adding more physics in there. And the key questions we're addressing are, whether these water-rich planets like the Earth can form around other stars, what conditions you need to form them, where should we look for them, can we guide these missions that are searching for them? And it really comes down to the question of, are we alone? Are there other Earths out there? Is there life out there? And the place we think that's good to start there is are there planets like Earth that might have life out there? So that is all I got for you guys. Thanks for coming to my talk. If you have any questions, feel free to ask right now. Or you can visit my website, or feel free to email me anytime. So that's it. Thank you very much. Oh.
away from the sun
How far away from the sun did the planets in our own solar system form? Jupiter, Saturn, and such.
That's all right. So the question is, how far away did the planet from the sun did the planets in our own solar system form? And no one knows for sure. People are looking into this right now, and it's thought that the Earth formed more or less locally where it is right now. Jupiter and Saturn are a different story. There's actually really interesting stuff that's been done lately. Jupiter and Saturn probably formed in a different configuration than they are now. Actually, all 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, probably formed in a more compact configuration. And I mentioned those giant planet instabilities that can happen. Jupiter and Saturn probably actually underwent one of those about 800 million years after the solar system formed. There's an episode in the moon's history, which we think is also relevant for the Earth, which is called the Late Heavy Bombardment. And so impacts on the moon are such that there's a big spike. We think there's a big spike in the number of asteroids and comets bashing into the moon about 700 or 800 million years after the moon formed. We think that also happened on the Earth. You just can't see it on the Earth because the Earth's surface is recycled much more. And what's the cause of that? We think the cause of that is actually this instability between the orbits of Jupiter and Saturn. And the instability wasn't so strong that one of them was chucked out completely, but it was strong enough to really destabilize these belts of comets and asteroids and end up sending a lot of them inward, and a lot of them bashed into the Earth and the moon. So where did they form? I mean, they probably formed in a slightly different configuration, but more or less where they are now. It's not known for sure whether they could have formed really far away and ended up where they are. But people are looking at that right now.
How can there be an instability between Jupiter and Saturn that ends in circular orbits?
So the question is, how can there be an instability between Jupiter and Saturn that ends in their having circular orbits? So their orbits aren't circular. They're about 5%, eccentricity of about 5%. And the way the instability between Jupiter and Saturn happened is quite different than the movie I showed you. The movie I showed you was just a couple planets and that's it. The instability between Jupiter and Saturn probably happened for a different reason. It happened actually because you had the giant planets forming here, and further out, actually, where Pluto is now, for example, it's called the Kuiper Belt. Out there's probably a disk of maybe 30 Earth masses worth of stuff. And basically what happens is because of scattering between giant planets scattering of that disk, it turns out that there's an interesting process that happens where scattering of these small bodies, asteroid-like bodies, causes the planets to move, kind of a reflex from that scattering. And it caused the orbits of Jupiter and Saturn to slowly separate. And the instability I mentioned is actually when their orbits crossed what's called the 2-to-1 resonance. So their orbits were initially closer. They crossed this resonance. The resonance is where the orbital periods are an integer ratio. So Saturn's orbit would have been exactly twice Jupiter's orbit. And then from there, they keep going. And so the instability is the crossing of that resonance. And that actually shakes things up quite a bit. But because of this belt of stuff further out, that prevented anything from going too crazy. That prevented Saturn from being completely ejected and that kind of stuff. The belt of material served to damp down the eccentricity. And in that process, lots of that cometary material ended up colliding with the moon and probably the Earth as well. Sure.
The moons of large planets, like in our solar system, Jupiter and Saturn, are they always going to be there? Do your simulations predict them? Are they as good as Earth?
That's a good question. I'm actually doing other research on that right now. So the question was, what about moons of large planets and how they form and evolve? Is that right? So we think that the large moons of Jupiter and Saturn, for example, probably form in little mini solar systems, basically. They form from little mini disks that are orbiting the giant planets as they form, just like the planets themselves are forming in disks around the star. And so they probably form in a similar process with interactions between the gas and smaller bodies kind of colliding to form larger moons. Do they survive for a long time? Well, they have for Jupiter and Saturn anyway. Would that always be the case? We're not sure. For example, if Jupiter and Saturn had had a stronger instability like the one from the movie, it's possible that they would have actually come very close to each other And in that process, that would have probably destabilized the moons of, the very close-in moons of Jupiter and Saturn. And also, as these planets migrate through all this rocky stuff, like in that movie I showed, there's lots of close encounters where things that are trying to build planets like Earth end up whizzing really close to these moons. And so in some cases, the moons can be destabilized. But we don't know for sure because we haven't seen any moons around other giant planets. But they probably survive most of the time, I would think, just given that we have so many large moons in the solar system. Sure.
I was just curious to kind of like summarize the search portion of it. So you're looking for planets that form at about the same mass in the habitable region of the Earth area, or temperature-wise, that also have the same ratio of water, or like, and you're looking for also like the right ratio of water to land. Like, is that?
Sure. I mean, that's a big question: is how Earth-like does a planet need to be to have life on it, right? There's a long checklist of things on Earth that seem to be good for us. We have about the right mass. We have a nice water content where we have both continents and oceans. We have these long-term feedbacks like plate tectonics, which drives various cycles which help with the climate. Do you need all those things for life? And the answer is you don't know. The simplest way to do it is to say you need, heat and water and some kind of building blocks. But then as you keep going, you could say, do you need a planet that's really Earth-like? And I like to think that you don't, but no one knows for sure. Or do you just need these relatively simple things? So for example, some people, I have some friends who hate the word habitable zone, and they go nuts every time I show these kind of pictures because, well, if you need a source of heat, it doesn't have to be from the sun, right? It could also be internal heat. So maybe there's a place, there's actually, Mars is not habitable, but if you go down a certain amount, then the pressure is large enough that you could actually have liquid water if it's there. And maybe the temperature's right as well. So there's kind of little habitable niches on various planets that might have life, and we haven't even probed it yet.
Okay.
So.
And then the other question I had was what is the nearest one of these? Like, how many light years away is it?
Oh, I forgot. I looked this up recently. I think the closest known planet is 4 light years away, maybe 5. Anyway, I don't know offhand, but it's a few light years away. Is the closest known star that has a planet of any kind. And right now, there's no stars that have known Earth-like planets. But the best candidate is that one I mentioned, Gliese 581. That's about 20 light years away. Typically, these searches are best for very bright stars, because what they do is they actually spread the spectrum out like crazy. So they need a lot of light to start with. So they need bright stars. So that means either close by stars or intrinsically bright stars. And so most of them are within, say, 100 light years or so. Any other questions?
Have you done simulations of multiple star systems?
Yeah, we have done simulations with multiple star systems. Right now, we're kind of applying these models, or one thing we're doing is trying to apply these models that seem to work pretty well for the solar system to a whole bunch of different cases and see what really matters. And it turns out in multiple star systems, things work pretty well as long as the stars are separated by a critical distance. So within some given separation, then the gravity of that second star is strong enough to disrupt everything. Beyond some given distance, then it's okay. And so it seems to work out okay. And there's other cases where you can even have planets around in a triple star system, for example. And it's the same kind of thing where you need a certain stability criterion to be met in terms of the gravity of all these bodies. And once it's met, then things work out okay. And you can map that onto what configuration of stars is okay for life, I mean. Other questions?
You say that as long as the binary has a sufficiently wide separation, then you can still get planet formation. What about very close binaries?
Okay, so close binary stars. It turns out it's the same kind of thing in terms of the stability. They have to be separated by a certain distance in terms of dynamical terms from the habitable zone or whatnot. And so very close binary stars are okay for having a habitable planet exterior that's orbiting both components of the binary. Or you can have a binary system where you're actually orbiting one of the binary stars and the other star's exterior to the planet's orbit. Either one of those works, and there's certain limits on the orbit of each binary component.
So it's pretty striking to me how in the data right now of just measured extrasolar planets, how large the eccentricities of the orbits are. And it seems, at least this is one way in which our solar system seems to be kind of very atypical, or relatively atypical, just looking at the distribution. I'm wondering if you could comment on that. Are we unique in some way that a big scattering event hasn't occurred, which typically occurs? And do you see in this distribution of eccentricities that we've now measured, are you reproducing that in your models, or do your models not really address that point?
Yeah, that's a big question, is whether we're normal or whether we're really unique. And it turns out in that distribution of eccentricities, the median is about 0.2 or 0.25. So half of them are relatively large eccentricities, but there's still a large number of planets out there that have kind of lower eccentricities like Jupiter and Saturn. And so I forget what the fraction of planets is that has eccentricities as low as Jupiter and Saturn. But it looks like we're kind of part of a distribution. And there's a couple planets that have been found just recently that have orbits very similar to Jupiter's in terms of both their large separation from the star and also being pretty circular. And so we think it's actually, it's very hard to find planets that are further out, because the amount of time you have to wait to discover a planet depends on its orbit. You have to see at least a full orbit, more or less. And so planets further out take forever to orbit their stars. Jupiter takes about 12 years. So if you wanted to find Jupiter around another star, you have to be measuring it nonstop, or not nonstop, but taking measurements over a time span of 12 years or so. And so those kind of planets are just now being discovered. And it looks like we're not the most normal case, because the median is something like an eccentricity of 0.2. But there are plenty of other planets out there that have eccentricities like Jupiter and Saturn. In terms of how those eccentricities got there, there's a lot of people thinking about that. And the current best model is that model I mentioned of instabilities between planets. So planets, we think, form on more or less circular orbits. And they form in the presence of these big gaseous disks. And the gaseous disks actually serve to stabilize the orbits a little bit as well. But they don't last that long. The gaseous disks last something like 10 million years or so. So the planets form. They're on nice stable orbits within this disk. Then the disk dissipates. And then the planets can become unstable after that. And so we think that the cause of the large eccentricities is largely due to instabilities later on. And we had an instability in our solar system, but it was a relatively small one. It didn't increase the eccentricity of the planets that much, just by 5 or 10%. Yeah.
What about organic material? What's part of that?
Oh, okay. So in terms of organic material, like how do you get it there?
How do you actually get life itself?
Well, that's a big question there. How do you get life itself? But in terms of organic material, I didn't talk about this very much, but the source of organic material is kind of similar to the source of water. So I didn't go into too much detail on there, but the main source of water on Earth, we think, was probably asteroids. The asteroid belt right now has very little material in it, but we think that early on in the solar system it had a lot of material. Most of that was cleared out by Jupiter, and some of it ended up impacting the Earth at a young age. And it delivered not only water, but lots of organic material, because lots of asteroids actually are very rich in organic matter. And so that's one source of organics, and also comets as well. So it's kind of similar to the water stories, that organics probably were delivered during formation. So the question was about the role of magnetic fields. In terms of the movies I showed, it has very little to do with it. The magnetic field is important for the planet migration process. Basically, the magnetic field the things that it can do that are relevant to what I've been talking about are, it can do things like carve a gap in the disk. So you have this disk of material around a star, and it basically truncates the disk very close to the star. It doesn't, the disk doesn't flow all the way into the star. It flows into it goes into a certain distance, and from that distance, material travels along magnetic field lines. And that can affect, in the end, it can affect the planet migration process. It can affect how fast planets migrate. It can affect where they stop in their migration. And so that, in turn, can affect how and where planets like Earth can form. And so it ties in that way. But in terms of directly affecting the gravity and the dynamics of planets as they form, it only affects that very inner portion. It doesn't affect things around where Earth is, for example. Any more? OK, well, thank you again. Cool.